Well, this is the most important lecture of this playlist, Inside-Outside Algorithm and Applications. So an example is an application of inside algorithm is this score that we use. So score of x, sentence x, and tree y, when we do constituency parsing, we always use that. And for any utterance x and graph y, we sum over scores of all constituents in the tree. And you can formulate this probability, this conditional probability like this: e to the score divided by this normalization constant, which is very difficult to calculate, but we calculate it with the dynamic programming, the inside algorithm that I will explain. So n is the finite set of non-terminal symbols, sigma is a finite set of terminal symbols, R is a finite set of rows, and the grammar is in Chomsky normal form. So each row takes one of two forms. It either goes to A, B, C, and either A goes to X. And S is a distinguished start. We always say S start, and we create the tree. So this is a context-free grammar that we are talking about in this playlist, and we want to parse it. Everything is usual, and we have rule productions. A rule production, for example, when we say this, it means that we split it A to B and C, and IKJ, it means that B is from I to K and C starts from K to J. So we split it like that. So when we say our rules, these constituents, these things that we create potentials in order to multiply them because they are independent to calculate the probability of a tree, are very important. For example, this tree contains the following rule productions. S goes to NPVP. 1, this is the first token, this is the second token, and token 4. Because we can name these tokens. 1, and for example, MP here is D and the constituents of that are D and N, and 1, 1, 2. It means the split is from here. And the potential of entire tree, as I said, because they are independent, when you're creating, you just multiply these, let's say, clicks, and because you can multiply them because they are independent. And psi is the potential of that. Potential, in physics, we use random fields. That's why conditional random fields in 2001 is originated from and inspired by physics, really. Even we use this in quantum field theory. I remember 10 years ago, and I was very interested in quantum field theory. We used to work on these things. So it's very important to know that this is very important. It also has physical meanings, not only in natural language processing. In everything, you multiply a set of potentials. And for example, this potential in here, because we are parsing, is just a rule, potential of a rule. And each one also has its probability, just like the normal probability law. And if you multiply it, this is just psi of t, but we have not normalized it yet. I'll give you an example. For example, the potential of going from S star to NP and VP times the potential of NP going to D and N times the potential of verb phrase going to V and P times the psi of D and 1 and psi of a noun, verb, and P, if you multiply that, it becomes the probability of this tree is proportional to this. So this is the probability of the parse tree under the PCFG, probabilistic context-free grammar. But we can define the potential like this. The potential e to the v times phi of r, and we just need to calculate these parameter vectors v. So the potential function of entire tree becomes this. Because there are many rows in the tree, for example, one row, the other row, if you multiply them, this is the potential. But the probability, we should normalize it to becomes between 0 and 1. Otherwise, it's not a proper probability function, and we have some problems with that. So the inputs to the algorithm are the following. A sentence where each xi is a word, a CFG in Chomsky normal form, and a potential function psi of r that maps any real production of the form to a value. And we define this to the multiplication of the potentials. So this is a beautiful application of that. As I said, in parsing, the graph-based approach to parsing, you should calculate the score. Once you do these constituents using neural networks, then you should calculate the total sum. But the problem of this probability is in this denominator, which is hard to calculate each time for all of these trees, because you're summing over all trees, it could be 100 trees for even one utterance. So that's why we need to be more clever and use dynamic programming, which is the most beautiful part of computer science, is dynamic programming indeed. And if we just calculate the alpha of S from span from 1 to n, then we are done. Then we can calculate this z, which is the denominator of this, and then we can calculate this, and the parsing, CRF parsing is done for constituency parsing. So the outputs of inside-outside algorithm is like this. These are the outputs because for our rule production, we calculate mu of r, over all trees and over all rows in each tree that we select. So it's a complex summation. That's why we are using dynamic programming. And for example, for non-terminal A, so for example, MP goes to something. And so this sum over potentials of T, but for all trees that A and IJ is in that tree. So the interesting note is that beta depends on alpha terms. So alpha, beta are like backward, forward, if you're familiar with HMM and many other problems in structured predictions. We use dynamic programming. So this is like that because they are coupled together. For example, in the inside algorithm, you go from I and J. So I and J is split by a K. So I to K is one constituent part. The other part is here. So if we calculate the alpha of I to the K, this part, and K plus 1 to the J, this part, multiplied by the potential of overall, then we can calculate. So it's a recursive things because we are going with higher constituents to more elementary constituents. And the inside-outside algorithm just uses these alpha because we are calculating beta, and beta is dependent on your alpha, which is the inside. So this is it comes from inside algorithm. So you see how the outside algorithm is related and coupled to the inside algorithm. And once we've done this for all A, then we're done. Then your outputs are ready and the denominator is ready and we can calculate all of that. So what is the interpretation of that? For each T has an associated potential, so we wanted to calculate psi of t. So alpha is nothing but summation of all these potentials. And also we can interpret beta because it's summation, but it is outer side. You know, alpha is the inner side, summation of inner side, but beta, of course, alpha beta in most of the text is quite the opposite, but it's just a name, alpha and beta, doesn't matter. The important thing is the concepts that I'm talking about in dynamic programming, and create a recursive structure. These variables you can say even psi and zeta and anything you like. So altogether, we had the problem, as I said, the denominator of that beautiful application. So now we can calculate it using dynamic programming very easily. And this is if we calculate alpha, then we can calculate z. So we can also calculate mu that I told you, because we should sum of the potential over all trees. It seems impossible, but we have done that. Then, so the mu is just a multiplication of alpha, which is your inside, and beta, which is outside. And altogether, we can say that for any constituents I and j, the mu, which is the summation of potential over all trees that have this rule on them, is just a multiplication of your alpha and beta. So the mu is just alpha and beta. If you do it for just one rule, you can calculate it like that. But you also pay attention to the potential that is constituent of that. So expectation maximization algorithm for PCFG, you can also, you see there are several papers that use this. So you need to know the expectation of something, expected counts for each rule, and now you have all the things that to do these calculations. For example, we can calculate the probability using just this counting, but so we can take advantage of these idea of dynamic programming, and this is the expectation maximization algorithm for probabilistic context-free grammar. And of course, parsing has lots of application. It has in computer vision, you can use it as well. And so it's not just for natural language processing. You can use it for music generation, in computer vision, speech, and even biology and bioinformatics. In DNA is the language, so you can use all of these parsing. You can do semantic parsing in DNA of your body. And so it has huge applications. And this is a great paper, I think, by Christopher Manning, if I'm not wrong. And this is another application in robotics that we could use these probabilistic context-free grammars. And he's an amazing scholar, Michael Collins.